All right, hello everyone. Welcome to our penultimate C prime talk of the semester. So my name is Tyler. If you haven't met me, I'm a graduate student here in the physics department, and I'm part of C prime, which is an organization designed to help promote equity, diversity, and inclusion in the physics department and beyond. And so one of the ways that we help to build community is through this talk series, where we usually have grad students give talks about their research in a way which is accessible to all. And so I am very excited to introduce Teddy today, who is just finishing up his PhD, and he's going to tell us about dipole rotor solids. So if at any point you guys in the room have questions, feel free to interrupt and ask them. And welcome everyone joining online as well. Be sure to monitor the chat. And for everyone in the room, we have plenty of pizza, so feel free to grab that. All right, without further ado, join me in welcoming Teddy.
All right, thanks for being here, everyone. I'm Teddy. I work down in the second basement with Professor Rogers in the condensed matter labs. We do a number of things, but my primary interest is in the study of dipole rotor solids, which are synthetic materials that involve trapping molecular machinery in order to create new kinds of ferroelectric materials. So this work involves a lot of serious chemistry, and without these collaborators, I wouldn't have things to use to make these materials. So I would first like to acknowledge Joseph Mickle, Piero Sozzani, and Jirka Coletta for all their hard work in designing and synthesizing the components of these materials. So we'll start by talking a little bit about my past. As a kid, I was always interested in learning, especially math, where we got to basically solve puzzles, and science, where we got to learn about things like dinosaurs and space and stuff like that. In contrast, I really struggled with reading and writing. And in kindergarten, I wanted to be a paleontologist, animal doctor in space. That obviously hasn't really been panning out, but it certainly seemed to point in a trajectory towards science, and probably had a lot to do with Jurassic Park and Star Wars being some of my favorite movies at the time. In fact, I have a real strong passion for film, all the equipment, the cameras, the lenses, as well as the practical effects that go into making things appear on screen the way they do. I also do martial arts, and so all the choreography that goes into movies is also of interest to mine. I love watching all the behind the scenes for movies. So in high school, I actually wanted to go to film school. And when I was looking at colleges, that's sort of what I had in mind of what I would do with myself. However, when it came down to applying to school, I caved and decided to apply to engineering schools for computer engineering, because that seemed like a much more stable, financially stable life path. Certainly feels like I dodged a bullet a little bit, just in terms of the fact that, it's very rare for a movie to be made for real anymore. They're basically just all animated movies anyway. So that was a very short-lived career. In fact, I changed to mechanical engineering before I even got to school. I think just the word mechanical invoked ideas of robots and engines and inventing gadgets and being creative, working with my hands more than just sitting at a computer typing away all day. And I really enjoyed the design, drafting, and CAD course that I took as a freshman, where I really got to work on the creative side of things, drawing designs and putting them into SolidWorks as well. However, I hated the repetition of my engineering coursework. I felt like I was just doing the same problems over and over and over and over with different numbers. And I felt more like I was being trained to be a human calculator than a creative individual. However, I didn't feel the same way about my physics and math courses. I actually really enjoyed these. And in my sophomore year, I took Physics 2. Who recognizes this picture? What is, I see some booze. I'm not surprised. Yeah, this is Gauss's law. And I missed this lecture going to a funeral. And so I come back to fail that next exam, which was super exciting. So in a panic, I started going to office hours for the first time. And I continued to go over the course of the semester, just making sure that I got all caught up and was able to pass the class. And in that process, I developed a really strong mentor-mentee relationship with that professor, and she ended up convincing me to switch from mechanical engineering to engineering physics. And I knew I made the right decision when in that same class, we went over this circuit. And who recognizes this or maybe knows what this does? Yeah.
Capacitor inductor.
And what does it do?
Yeah.
Does anyone know the name of this circuit? It's a resonator circuit. And it oscillates with the following frequency. And so basically you charge up the capacitor, it discharges through the inductor continues to carry the current even once the capacitor is discharged, charging it back up. And so you get current sloshing back and forth in the circuit. And I remember thinking, wow, it's so cool that the mathematics behind the mass on spring also applies to something not mechanical at all, and that you have these overarching ideas in mathematics that can apply to multiple physical phenomena. And then someone had raised their hand and asked the question kind of in a snarky tone, well, what's that useful for? And they were obviously an engineering student. And I realized in that moment that although I did care and find the answer to that question interesting, I didn't find it as interesting as all the other things that I had just been thinking about with the mathematics and the parallels across different kinds of systems. And then I would actually, yeah, go ahead.
What is it useful for?
I was kind of expecting that. Well, it can be used to set frequencies. And so the resonance frequency of the circuit can set frequencies. One specific application is that this is used in radios. And so the tuner dial on the radio is actually a variable capacitor. And so you change the resonance frequency of the resonator to pick up the different channels. And so I would actually go on to then drop the engineering part of my engineering physics, and I ended up finishing my degree in math and physics. So I basically traded off the engineering classes for more math classes. So, and so Gauss's law, I know a lot of people hate it, but it will always hold a special place in my heart because it set me on the right path and also kind of opened my eyes to the value of office hours beyond just like trying to catch up, and that, you know, it's a really valuable resource. And so here's me in the lab that following summer. So this is a lab at Stanford where I was working with that same professor who was collaborating there. And we were looking at superconducting sensors. And so I was doing a lot of electronics in there, very much akin to what you guys do or would do in junior lab. We took that, basically the equivalent of that class as sophomores, so I was already prepared for that kind of stuff. And then the following summer, I was also doing some data processing with Python. So then I applied to grad school. I got in here. This is where I wanted to go, but I ended up taking a year between, and I was working at NIST just down the street. And so there we were also using superconducting sensors, but in applications for quantum information. So I was involved with some of the fabrication and assembly steps. And then I also was building up some vacuum systems for the cryostats to run the things. So now to get into the meat of the talk, I don't really expect anyone here to have heard of a ferroelectric before. So what I want you to do is turn and talk with your neighbors and discuss what you already know about ferromagnets, which maybe you know some things about. So go right ahead. All right, so hopefully you had enough time to discuss a little bit about it. Does anyone want to share out something that they discussed? All right, that's fine. We'll just talk about it. So a ferromagnet is a material that can be spontaneously magnetized. And so you're familiar with these materials in the fact that you interact with them almost on a daily basis. These are anything that is a permanent magnet. They're in the lids of our laptops to hold them closed. They're the fridge magnets. Literally anything that is a permanent magnet has a spontaneous magnetization. And this is a reversible process. So, sorry, first, so here we have a bar magnet, and then we can see kind of the iron filings align with the magnetic fields. And so we can see that there's sort of this dipole field behavior that this thing has. But what makes a ferromagnet is the fact that it goes through this hysteresis loop. And a hysteresis loop, history, basically means that the result you get at measurement depends on the past. And so here we can start at the origin where there's no magnetization and no applied field. And then we can go through A, B, C while we apply a strong magnetic field. And then when we remove the field, we go to D where there is a spontaneous magnetization, leaving it as a permanent magnet. And then we can remove that magnetization by reversing the field to E and then continue to F and then turn off the field at G. And now we've magnetized the magnet in the opposite direction. So a ferromagnet is defined by going through this hysteresis loop. Now, ferroelectrics are a type of dielectric material. So I want to review dielectrics real quick. This is just the simple scheme of dielectrics that we've probably seen before. We have a material represented in balls representing the atoms. And when we apply an external field, this is going to stretch these. It's going to push the positive nuclei and pull the electron cloud. And each of these is then going to be little induced dipoles, with the dipole moment being related to the charge and the distance that you stretch the thing. And this would not go through a hysteresis loop. When we turn off the field, the polarization is also going to go away. And so the relationship between the polarization and the electric field will just be this linear response with no hysteresis. So a ferroelectric then would be a material that goes through the hysteresis loop we discussed before, where we can have a spontaneous polarization with no applied field, and this can be manipulated with external fields. And so here's an example of a naturally occurring ferroelectric. This is a perovskite crystal structure unit cell. And what makes it a perovskite is the fact that on the corners of the unit cell, there are these positive ions in blue. And then on the faces, we have these negative oxygen ions in red. And then in the center of the unit cell, we have this green positive ion. And for reasons that we don't have time to get into, this green positive ion does not like to sit dead center in the unit cell. It always wants to be kinked in a particular direction. And this kink is going to induce a local dipole moment because you have a positive charge which is moved relative to negative charges. And so this is going to form domains of polarization. So you're going to have these regions or chunks where each of these ions is jumped into the same position within this chunk, giving it a polarization in a particular direction. But when you add up over the whole crystal, you may get no polarization, leaving us at the origin on this graph. But then you can apply an external field and get these domains to align, basically shifting all the ions in each of their unit cells to the right in this case, and giving it a spontaneous polarization that persists even once the field is removed. So some reasons why ferroelectrics are maybe exciting for some people is that they have, for one, anomalously high dielectric constants. And who could think of maybe a reason why that would be useful to people? Yeah, capacitors. So capacitor values scale by the dielectric constant of whatever you put between the plates. And so by putting a perovskite or a ferroelectric in general between the plates, you can make ultracapacitors, which I thought used to be called supercapacitors. I guess the name changed, but regardless, these are used in like electric cars, for example. When in the braking system to recharge the battery, you can't directly recharge the battery that quick, you'll fry it. So you charge supercapacitors first, and then those can take the charge much more quickly, and then those will slowly bleed out into the battery. Another thing is all ferroelectrics are also piezoelectrics, but not all piezoelectrics are ferroelectrics. And the piezoelectric effect is just a relationship between voltage and stress. So you can push on a ferroelectric or a piezoelectric, and that's going to induce a voltage across it. And you can also apply a voltage, and that's going to strain and stress the crystal structure. And so this is a way to exchange electrical and mechanical energies, which has lots of applications. One we will go over a bit later. And then the hysteresis itself has applications. What do you think the fact that it goes through this hysteresis loop, what can that be useful for? Ferromagnets are actually used in the same way. Yeah.
So a question, with this piezoelectric, should I imagine that you're pushing on this unit cell, you're changing where the green atom is, so that's somehow shifting around the voltage of the entire material?
Yeah, the voltage is going to be related to that polarization.
Okay.
Because when you do have a polarized crystal, that's going to have a voltage across it. So it's almost like just using different language, like whether you're talking about electric fields or you're talking about voltage, is sort of, they're intermingled. So ferromagnets are actually used in hard drives, which I guess are not as used as they used to be, since solid state drives are kind of taking favor. But so this can be used for memory. Basically, you can have it in one state or another state, measure it, and have one represent 0, have one represent 1. And this is actually how RFID chips work. They have ferroelectrics inside storing the information. So we discussed dipole moments that were induced by moving charges, but we can also have dipole moments that are inherent to a system. And these come in the form of polar molecules. So this is my favorite polar molecule. It's water, an oxygen and 2 hydrogen atoms. And because it has this kinked shape, gives it almost all of its interesting properties, including its dipole moment. And so what is a hydrogen atom? It's the first one on the periodic table. So what's it composed of? Well, what goes into hydrogen? It's just 1 proton and 1 electron, but that electron gets used up in the bond. And so this electron belongs to the hydrogen, but it's going to live sort of in this region. And so that is going to basically we can think of a hydrogen atom as being a proton sticking off of our molecule. So we can think of the hydrogens in molecules as just basically being hanging off positive charges. And so if I showed you this picture, could you tell me the direction of the dipole moment? It's a little tricky. Yeah, it's down. It doesn't go in the direction of the internal field, it goes in the direction of the external field. And so this dipole is then going to create this familiar sort of butterfly wing shaped dipole field. And so then we can imagine taking a bunch of these water molecules and throwing them down on a surface. Here they're represented in arrows pointing in the direction of their dipole moment. And in this system, we're forcing them to live on a 2D triangular lattice. Remember, lattice just meaning geometric pattern. And so each of these dipoles is then going to produce its own field, and these fields are all going to torque on all the other dipoles. And so we call this dipole-dipole interactions, and these are all going to influence each other into rotating into a particular way. And so this is actually a Monte Carlo simulation that I ran, and after a certain amount of steps, we can see that domains start to form. And then we can apply an external electric field and make all the dipoles align. And then removing the field, we can see that the system stays polarized. So this system of rotatable dipoles on a 2D triangular lattice is a ferroelectric system. Now, why would we want to build such a system when ferroelectrics already exist? Well, for one, this exhibits ferroelectricity in a new way. So we're able to probe interesting physics that isn't testable in other states of matter. But also, this has an additional property that other ferroelectrics don't have, and that they're able to propagate very slow sound waves. So we can imagine one of these dipoles flickering in dipole angle. And so that's an oscillation, and that's going to influence its neighbors to also flicker in dipole angle. And so this will result in a very slowly rippling flicker wave across the material. The speed of sound in solids is typically very fast because it's mediated by very tight bonds. And so slowing sound in solids actually has some interesting implications. And to understand why, we'll have to talk about acoustic wave resonators. And I don't expect anyone here to have ever heard of these things, because I I certainly hadn't before working in this group, but we carry them around with us everywhere we go. They live in our cell phones. And you can see with the Penny, this Qualcomm chip, which has the resonators in it, they're quite large and take up quite a bit of the real estate on the motherboard. And so what do these things do? Well, they create the stable voltage frequencies in the phone, which are pivotal for filtering and picking up signals from cell towers. And so these are crucial components of our phones, and they utilize the piezoelectric effect to resonate a crystal mechanically, and that mechanical resonance is going to set that stable frequency. And so the size of the crystal is then dictated by the frequency that you want and the speed of sound through that crystal. And so slowing sound in a solid would allow us to make smaller resonators. And remember that since the system that we discussed was ferroelectric, it inherently must be also piezoelectric. And so how are we going to do this? Well, we'll start by talking about dipole rotor molecules. Here's a diagram of one. I don't really expect anyone in here to be able to read chemical diagrams, so we will turn it into more of a ball and stick model. And here, the yellow is carbon, the nitrogen is, or sorry, the blue is nitrogen, and the pink are our hydrogens or protons just sticking off of the molecule. And so if I told you this central ring was the dipole, could you tell me the direction of the dipole moment? Yeah, it's this way. Or sorry, that way. On my screen, it's this way. It's yeah, it's to the right, in the direction of the positive charge sticking off of that group. And so there's the dipole moment, and then this ring is able to spin like so on the bonds to the end group. So chemical bonds are actually, kind of slippery in a sense. And so this ring is able to take multiple orientations relative to those end groups. And so then we can think of the carbon-carbon bonds as axles and the end groups as stators. And we can then just represent it as this cartoon here, where you have stator end groups, and then a dipole is able to rotate about axle-like bonds. And so to make a dipole rotor solid, we just take a bunch of dipole rotors and we trap them in a host crystal, represented in cheese here. And so the cheese or host crystal has these wide open channels that are large enough to fit molecules inside. And so we're able to then to trap these dipole rotors in a particular orientation to force them to rotate in a particular way, and also onto a particular lattice structure. And so our weapon of choice for this is trisophenylenedioxycyclotriphosphazine, which is a bit of a mouthful, so we just call it TPP. And TPP is a 3-blade propeller molecule that forms into crystals. And so here are 2 layers of that crystal. Each is rotated 180 degrees from the last. And so when you stack them up, you can see that it makes a honeycomb. And it's a honeycomb bilayer because it takes 2 layers to make the unit cell. And then we can define the honeycomb constant as the distance between the channels. And so this is one of the lattice parameters. And then the other lattice parameter would be the distance between the bilayers, which we can call L for layer constant, and that's about 1 nanometer. The honeycomb constant can actually stretch depending on the size of the molecule that you fit into the channel and how much of that molecule you fit into the channel. And so this can range anywhere between 1.1 and 1.2 nanometers. And remember, nanometer is 10 to the minus 9 meters. And then the channels you can clearly see lie on a triangular lattice. So any dipole rotor we fit into the TPP channels is going to be forced to rotate in the plane and also be forced to live on a 2D triangular lattice. And so now getting into some of the stuff that I actually do, this isn't all of it, but just some of the things that I do more often than others. I grow thin films. I do atomic force microscopy to image surfaces, X-ray crystallography to measure lattice constants, dielectric spectroscopy to essentially probe the dipole dynamics. I fabricate my own capacitors, and as of late, I've been doing a lot of cryostat modifications in the machine shop. So this is what TPP powder looks like. It's just a white powder, and when I started working in this group, we had only ever studied these materials in powdered form. And there's lots of things that you can learn, but one of the things that you can't learn is the dielectric constant. And we'll get into why a little later. So here's my film growing chamber right here. It's just a bell jar that I can pump on the bottom of. And inside there's this, what we call a boat. It's really more of a kayak, but it's clamped down to these electrodes that I can run current through to heat it up and evaporate whatever's inside the kayak. And so I can then take some samples, some substrates here, a silicon substrate and a glass substrate with capacitors on it. And I can put those up above the hull of the kayak and try to catch whatever vapor is coming out. And so then I can tape these down so they don't fall, so it's going to be upside down. And this is the result. So you can clearly see where the silicon is, where the tape was holding it down. And then you can see that something is clearly growing. Now, this sort of greenish yellow color is actually coming from the fact of like an oil spill effect, really. So you're basically you're not seeing color based on atomic structure, you're seeing color based on thickness of a very thin film. And so the fact that this is relatively uniform in color tells us that the thickness is relatively uniform as well. But to get a more quantitative result for that, I can take this over to the AFM, the atomic force microscope. Now this instrument is over in Gilla in the Keck lab, and it takes a very tiny tip and it vibrates it over the surface. And through van der Waals interactions, it's able to, the surface basically pulls the tip up and down with the contours of that surface. And by reflecting a beam off of the back of the thing, you can then detect the deflection of that beam to measure the exact position of that tip as you drag it over your surface. And so here's some results of AFM images. On the left here, we're at a 10 micron scale. So 10 microns being 10,000 nanometers. And what we're seeing here is actually the transition of the edge of the film. And so this is where the tape was. And I took this picture because I wanted to know the step height, to know the film thickness. And knowing the film thickness would allow me to then quantify the dielectric constant, which we'll get into later. But what we can see here is that there's actually these snowflakes of TPP crystal forming out underneath the tape. So this basically means that when a TPP molecule lands on the surface, it still has some mobility. And so it's able to rotate and sort of scatter around and kind of fling itself underneath the tape. So that's why we can see some crystallites forming. And then here is an image somewhere in the middle of the film. This is about zooming in 4 times. And we can see some evidence of these snowflakes sort of forming here. And so what this tells us is that the film is not a perfect single crystal all the way across, but rather polycrystalline or many crystals. And so at this point, we know that there's many TPP crystals forming, but we don't know if they're oriented, right? So ideally what we would want is for layers of TPP to sort of stack on top of the surface. And so in order to find out, we need to take this over to the X-ray diffraction device on the 2nd floor of Duane. And so here we just blast a sample with a beam of X-rays. You can see a beam stop, which stops the beam from burying into our detector. And our detector is basically just a camera sensor with many pixels. And so if we do this with a powder, the powder is going to be randomly, each little crystallite will be randomly oriented. And so what we should expect to see is rings. And these rings are basically mapped out because we're getting diffraction in every direction due to crystals being oriented in each direction. So the rings are an indication of random orientation. And the important thing to know here is that the radius of the ring is inversely proportional to our lattice constants. And in fact, these 2 rings here correspond to our honeycomb lattice constant, which is based on this radius, 1.1 nanometers, and above the layers are stacking individually at 0.5 nanometers, giving a layer constant of 1 nanometer. And so I can also take a film and put it in the path of the beam. And this is actually quite a bit tricky because there's not a lot of material to interact with. And so the beam itself, so to get maximal interaction, you actually have to tip the sample just right so that you get total internal reflection. and you get the beam basically scooting along the surface of the sample, getting maximal interaction. And this is the result. You can see that the signal to noise isn't that great. And in fact, on the projector, it's really hard to see the bright spots at all. And that just has to do with the fact that there's just not a lot of material interacting with the beam. But the fact that we don't see full rings is great news, because that means that our polycrystalline film is not randomly oriented. And in fact, there's these two bright spots here that maybe you can kind of sort of see. And because they're on the x-axis, and because they're at a distance that corresponds with the honeycomb layer or honeycomb constant, this tells us that the honeycombs are separated along the x-axis of the surface. And then this bright spot on the vertical is at just the right distance to correspond to our layer spacing. And the fact that that's on the vertical of the detector tells us that the layers are in fact stacking on top of each other. And so at this point, we know that our polycrystalline film is aligned in a way that is convenient for us. But at this point, we don't know whether or not there are actually dipole rotors inside the channels. All we know is that we have a honeycomb crystal. And so in order to find out, we have to do some dielectric spectroscopy by measuring capacitors. So this is my capacitance bridge. It's really precise. It's so precise, they even wrote ultra precision on it. And this first digit here is a picofarad, which is 10 to the minus 12. And so that last digit there is 10 to the minus 18 farads, or an attofarad. So this is a very, very precise bridge that takes great data. And so why am I measuring capacitors? Well, as you may know, you charge up a capacitor in proportion to the voltage that you apply, dictated by the capacitance. And so when that happens, you get these electric fields inside. And any material you put in the electric fields will interact with those fields, induce dipole moments, and change the value of the capacitor. And so we can think of capacitors as something that depends on dielectric constant and geometry. And does anyone remember the geometric dependence for a parallel plate capacitor? Yeah. The area of the plates divided by the distance. And so that's the geometric dependence for a parallel plate capacitor. However, parallel plate capacitors would be really difficult for me to use, even though the mathematics is very simple. So instead I use what's called an interdigital capacitor. And it's called that because it has these interweaving fingers or digits. And so the convenience of this is that I can just put a material on top of the fingers, and fringing fields will interact with the material and change the capacitance. The mathematics of that is really complicated, so we won't even try to get into it today. But here is an example of a rotor solid powder. And so this is TPP with rotors inside, and you can see that the color changed a little bit, and that's pretty typical. Sometimes they're a little pinker or grayer or browner. And then you can plop it down on a capacitor structure and measure how it changes the behavior of the capacitor to learn all sorts of things about the dipole dynamics. And I used to do this in this probe station here. And so this is just a really nice system with these probes that you can control with micrometer dials and drop the probes down on a capacitor. In fact, you can see the probes kind of coming in right there. And then I can run liquid nitrogen through the straw and cool down the cryostat. And it always makes these nice little ice balls. And so here's some data as a function of temperature and frequency. The different colors are measuring at different frequencies, and the x-axis is temperature. And we can see that depending on the end groups of our dipole rotor, we get different results. But the issue here is with powders, it's really impossible to compare the exact value of capacitances here and say which one has more dielectric constant. One could have thicker powder, and it's really hard to know like how much free space is between the crystallites. So comparing the capacitance to the dielectric constant is kind of impossible here. But when we take measurements on films, we can see that we still have the same sort of behavior here where the dielectric constant drops off rapidly at low temperatures. And for For this, we can just think of this as basically the dipoles freezing out and no longer able to rotate. And when they're no longer able to rotate, they don't contribute to the dielectric constant. And so down here, we're basically just measuring the dielectric constant of pure TPP. And this feature is super important to measure in terms of actually learning things about the dipole rotor behavior. And it happens at about 50 Kelvin. And who here knows what the temperature of liquid nitrogen is? Yeah, it's about 75 Kelvin. And so 75 Kelvin gets me right about here, which doesn't get me cold enough to resolve these peaks. This was taken with liquid helium, which, as you may know, is becoming a lot more expensive and harder to come by. And so it's becoming very expensive to do this experiment. And so what I've been doing is moving my system over to a closed loop system so that I can not use liquid helium. I can just use a compressor in a refrigeration cycle to make liquid helium on demand, essentially. And so this is the first cryostat that I tried to utilize. It's just a little dinky single stage cryostat. So it goes through a refrigeration cycle with helium to get the stage down to, as you can see, roughly 50 Kelvin. And you can see by the data that it's not a very good system. The noise is sort of all over the place, and this is happening because of the vibrations. So this is a refrigeration cycle. So there's mechanical oscillations happening. If you've ever been in a lab with one of these running, you would definitely know it. It goes ka-king, 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 ka-king. And so it's basically just rattling the whole thing constantly. And so that's where the noise is coming from. And so I've moved on to pulling this cryostat out of the hallway, which someone didn't need anymore. This is a little nicer. It's a 2-stage. So at the bottom there, you can see the first stage, and then there's a whole nother refrigeration cycle happening on top of that to get that top stage even much colder. And then you can see a flange here that someone had already made to raise access to the stage. And then there's this clamp here as well. And so this whole thing fits into this tube here. And then this bigger tube is a nitrogen trap. And so whoever was using this before would just pour liquid nitrogen into that. And then as that's boiling off, it's just cooling down something underneath. So let's flip it over and see what's inside. You can see here that there's this aluminum shield, which the trap is cooling. And then this copper strip runs off to our cold head. And then this is just a sample stage that you can mount things to cool down. So the issue here is that I want to use it in this orientation. And there is immediately a serious problem in that the nitrogen trap is now completely useless because it would just pour out all the nitrogen. And the reason why I want to use it in this orientation is so I can take the lid off and swap out samples rapidly. And so the first step is to isolate the shield and then attach it instead to the warmer of the two cold heads. And so here, this is actually the second or third attempt at this. This is just a custom L bracket that I made to meet the face of a cylinder, and then a copper block that could then run to the warmer of the two stages here. And so then you can still see that copper strip running to the other stage. And then the other issue is that the distance between the top of the stage and the lid is about 0.4 inches, which doesn't leave me a lot of room to make a sample mount and make connections to it. And so I attempted to do all that in the small amount of space, and I wasn't really happy with the design. And so I decided to start over, pull out the stage, and just mill out a giant pocket to give me more room. And so then I need to design a sample mount. And so this is what I came up with. It's just something where I can wire bond between these pads and the capacitors. And then I can take the sample mount and bring it between a bunch of different experiments, a microscope, the AFM, and then inside the cryostat. And so then I need to be able to make connections to that thing. And so this is what I came up with. It has these spring-loaded pins here and just really simple circuit running those pins to connectors. And then I milled out these sort of, I don't know what to call it, pockets, I guess, so that I don't short out my circuit. And so those sandwich together to make what I call the sandwich lid. And these pogo pins are then able to meet the these paths here and make connection. So then I can then take some SMA connectors and run them out to my bridge. And this is the result. And you can clearly see that the data is much cleaner. The fact that everything is not directly attached to the cold heads makes it so that the all the vibrations are, as you can see, dampened out by the time they get to the capacitors. And so in summary, rotor solids are crystals with rotating parts. AFM is a tool that we can use to image surfaces and quantify heights. XRD, or X-ray diffraction, is a tool that we can use to measure lattice constants and as well as orientations of crystals. And dielectric spectroscopy probes that dipole behavior, but I need thin films to allow me to quantify the dielectric constant. The thin films having a uniform geometry allows me to calculate through complicated calculations what the dielectric constant must be to contribute to the capacitance in the way that it does. And then sometimes scientists have to be engineers, and that's okay. And so I've been spending a lot of time with these cryostats. You pretty much just got to see finished products. I didn't have time to go over all the steps along the way. But yeah, so that concludes my talk. Thank you for coming. And does anyone have any questions?
So how would you calculate this?
Okay, so let's see. So the question was essentially, we've got dielectric constants that are related to these induced dipoles. And we also have hysteresis, which ought to affect the behavior depending on the frequency that you apply. Actually, I'm going to go, let's see, I have a bunch of slides in the back that I took out. So I think that this sort of answers your question, I think. So essentially what should happen for these sorts of systems is that once you go too high in frequency, the behavior can't keep up, essentially. And so you get the real part of the dielectric constant dropping rapidly. And that is essentially what is causing the fall off that we see in temperature, because this thing will shift as a function of temperature as well. And so even at lower frequencies, as we shift the temperature, this whole thing will move down to lower temperatures. And then this will also be associated with a peak in the absorption or the dissipation. And that's actually the real measurement for the powders is quantifying the location of these peaks. And so each of these peaks disperse as a function of the frequency. And so each frequency will have a different location for the peak, and then you can essentially fit all that to that equation there, and that gives you essentially what the barrier to rotations are, and it pretty much any time you have something that can inhibit something's ability to change state in a dielectric way, this equation in this scheme will basically tell you what that barrier is. Oh, does that answer your question at all?
I think that's it's better. I still have a question.
Okay.
So in that case,
Yeah. So I'm not sure I understand the question, but in terms of like doing an experiment to get the hysteresis loop out, we're not doing that currently. And so from a technical standpoint, we haven't done an experiment that proves ferroelectricity yet. So far, all we've been able to do is probe the the behavior of the dipoles rotating inside the systems. And so that is a future experiment in terms of one trying to essentially saturate the system, getting all the dipoles to line up, and then increasing the field more and more and seeing that it's not changing the dielectric constant, or it's not changing the voltage. And so, yeah, there's definitely more experiments in terms of like proving that this thing is ferroelectric, but right now we're really more studying the molecules inside more or less and their dynamics inside the crystal. In general, oh, I don't know. What's my favorite material? Let's see. I don't know. Yeah, plastics are pretty nice, I guess. No, I'm just kidding. No, these are definitely cool. So some of these, what we can talk about, these are actually super cool. They are what we call dipyridazine rotors. So pyridazine is just the part of the molecule that is the dipole moment. And so these are basically long polymer chains. And so these actually can't exist outside of TPP. So this part of the molecule here at the center is chemically explosive. And so these things will just spontaneously pop if they're not in TPP, but for whatever reason, living inside the channels keeps it stable. And the reason why we study these ones is because they force certain spacing between the layers of dipoles and by forcing them onto one chain. And they're so at like a 9-state model, as we call it, which is there's 2 9-state models that you can think of like 2 dipoles being above each other. So if one plane of dipoles is all aligned ferroelectrically, then the next plane wants to be anti-ferroelectric to that, pointing in the other direction, because the fields kind of wrap like this, and so they start to point backwards. And living in the TPP channels, you have these basically 3 directions the dipole wants to point because of the blades, but each layer gets rotated 180 degrees from the last, and so those 3 directions shift. And so so depending on the length of that double rotor molecule, you can force them to live in potentials that force them to align versus a different length, which forces them to anti-align. And so we can actually see, I didn't include plots for it, but we can actually see very different, inconsistently different behavior of the rotors, depending on whether they live in symmetric or anti-symmetric wells. So those ones are pretty cool. I think this powder is actually one of them. Oh my God, so many slides. That one is one of the double rotor molecules. Any other questions?
How has your work affected your appreciation for the fundamentals that got you to this work? For example, you now understand dielectrics and capacitance far better than you probably did when you started, or maybe
Yeah,
molecule or something like that.
there's
You think back on things that you learned a while ago with the appreciation now that you do this.
I think for me personally, the more I get more value out of just the process and the techniques and the different systems and experiments than learning things about these super obscure materials themselves. So like, you know, operating the atomic force microscope or the X-ray diffraction system and all that, because you know, all pretty much any solid state physics you do, you're going to be doing X-ray diffraction. You're likely going to be doing it. Dielectric spectroscopy is a little bit of a more obscure experiment, which is why people sometimes send me samples to do dielectric spectroscopy on that have nothing to do with any of this. But yeah, I mean, I think learning about, even though it has really nothing to do with this research, other than the fact that it's also ferroelectric, I think learning about perovskites has been super interesting. There's all sorts of cool things going on with perovskites because they also exhibit essentially like solar cell behavior. And so you can excite current or electron transport through shining light on it. And there's all sorts of exciting things there because it's basically just like a simple mineral structure that's like deep in the crust, and you can, with chemistry, build it yourself. But it's like this, it's not an obscure material, it's cheap to make, and it can be used to make solar cells. The issue there is like, well, there's lots of issues there, but you know, it's ongoing research actually making it work for like large scale industry applications. But it's a pretty exciting field. So learning about all that has been super cool too.
Cool.
If anyone else has any other questions, feel free to come up front, talk to Teddy. But if not, join me in thanking him one more time.